So, welcome everyone to our cochlear seminar today. My name is Jennifer Deal, and I'm happy to welcome everyone, and we'll get started. So thank you so much. Welcome. We're glad that you're here. So we're really delighted to welcome Dr. Jeanette Mahoney today to talk about multisensory integration in healthy and pathological aging, links to cognitive and motor functioning. Before we get started, just a couple of announcements. So there is a Q&A option for the seminar today, and the questions will be held after Jeanette's talk. If you are online, we ask that you please use the Q&A feature that's available on the webinar, and then we'll ask those questions on your behalf. The questions that you put in that Q&A function will be sent to the panelists only. We do have closed captioning available, CART services, so there is a link provided here if you'd like to access that transcript. Just to let everyone know, this seminar is being recorded. And if you do have any technical difficulties, please let us know. And you can do that by directly emailing the email here on the screen, the JHU Cochlear Center at jhu.edu. So just a reminder for the remainder of our seminar series this academic year. So today we're again very glad to welcome Dr. Mahoney. And then please do save the date for our upcoming seminar. And this is our research day, which is our annual Cochlear Center Research Day. It will be held on Friday, April 25th, starting at 9 a.m. and running all the way to 4 p.m. And that is because we have a full day of events planned. We will also have a keynote address around lunchtime, which will be Dr. Laura Nyplade from RTI International. And we're very excited. She's going to be talking to us about some of the work that she does around stigma, in particular, how she's applied some of that work to hearing loss. So please do plan to join us for that. Please mark your calendars, and you can expect to get more information on that from us very soon. So with that, then, I'd like to go ahead and welcome our speaker for today, Dr. Jeanette Mahoney. She is professor and chief of the Division of Cognitive and Sensory Motor Aging at the Renaissance School of Medicine at Stony Brook University. Dr. Mahoney received her BA from Stony Brook and her PhD in clinical health psychology with a minor in neuropsychology from the Fairclough Graduate School of Psychology in the Bronx, New York. After that, she completed a postdoctoral fellowship at the Albert Einstein College of Medicine, where she stayed and worked her way up in the ranks to be associate professor before recently making her move to Stony Brook. She has a lot of primary interests in terms of her research that overlap a lot with the work that we do at the center, including healthy aging and sensory function, and in particular, multisensory integration, which she'll be talking to us about today. As well as its connections to cognition and to falls risk. Her research objectives include determining how to optimize the integration of multisensory inputs for older adults, with this goal then of falls reduction, improving mobility, and helping older adults maintain their functional independence. She is also the founder of the JET Worldwide Enterprises, Inc., which is a digital health startup, spun out of Albert Einstein College of Medicine. And she has developed a novel fall risk assessment tool called Catch You Before You Fall, which I'm sure we'll be hearing about today. And Dr. Mahoney and I also have a chance to work together. So she helps co-lead the Sensory Health Working Group at the Gerontologic Society of America as well. So thank you, Dr. Mahoney. Welcome. Thank you. Thank you, Jen, for that kind introduction. And thank you guys for having me here. I'm happy to be here. Talk to you a little bit about my journey over the past 15 years or so. Feel free to interrupt me. You can stop me. It doesn't have to be formal. And you can let me know if I'm talking too fast, because that just always happens here. So I do have some disclosures, as Jennifer mentioned. I do have my own startup. Most of my work that you'll see today is supported by the National Institutes on Aging and some additional funding I had from the Resnick Gerontology Center at my former institution, Einstein. So these are my objectives for the talk today. I'd like to introduce the concept of multisensory integration to you guys. Has anybody heard about it before or used it in any work?
Great. So we'll provide an overview, don't worry. I want to demonstrate the importance of studying multisensory integration and how it has profound impacts in aging. In particular, there's other populations I will specialize on in some topics in aging today. I'd like to describe a potential overlapping neural network that's involved in multisensory integration and how it has impacts with concurrent overlaps for cognitive impairment and what we call preclinical Alzheimer's disease, which can really be conceptualized as mild cognitive impairment. I will then provide some of the details of my current R1 that I left at Einstein. Talk to you a little bit about moving beyond the lab, because I think it's every researcher's dream to get their research out of the lab and to the people that need it the most. So I'll share a little bit of the clinical translational journey I have with trying to get Ketchu to the market, and then provide details of some upcoming research endeavors that I'm currently working on. So what is multisensory integration? It's a really cool word, right? But do we really know what it means? Every moment of our lives, no matter where you are, you're constantly bombarded with tons of information from all of our sensory systems, right? And that information is designed to be efficiently processed by our brains in a concerted manner. It's not like you're listening to me first and then you're looking at me and all of that information is serially making its way to the brain. It's coming in a parallel manner, and our brains are designed to efficiently integrate it so that we can successfully respond to these modalities appropriately. It might be the difference between identifying something quick enough or accurately or responding to it in a way that would make sense. So the reason why I think it's so important to study it in aging is because that over 3 million older Americans, this number is probably even more than that, but they require an emergency room visit every year because of falls. Falls are a huge problem. We spend a ton of money on falls. And poor balance is one of the the major predictor of falls, which is a leading cause of injury and death in aging. So it's something that we need to get better at recognizing and help before it happens. Age-related unisensory declines, so declines in hearing, declines in vision, declines in our ability to feel things, they've each been individually linked to worse motor outcomes. And why this is important is balance in and of itself is one of these motor commands that require this efficient interaction between our sensory systems and our musculoskeletal systems. And it's especially important across the visual and the somatosensory and vestibular, which I will argue is a sixth sense, to control everyday movements. And these systems are each individually compromised in aging. So there is evidence to support that multisensory integration could be a compensatory process used to overcome age-related physiological declines in unisensory processing. My take-home message, which I really hope you'll understand before I leave, is it possible that there is some underlying neural mechanism that's responsible for age-related decline that concurrently impacts sensory, motor, and cognitive function? Every day, you guys all have phones. Every day, we are receiving inputs from these multisensory things. I thought I'd show you some examples so you can relate. Some people just like their phone to ring. If you're like me, the volume's never on and it just vibrates. But some people like to have it lighting up, vibrating, or sound, or however many sensory stimuli they need in order to respond to their phone call, right? So the more sensory modalities you have turned on your phone, the faster it is you'd likely pick up that phone. Other sort of safety things that are multisensory in our world include backup cameras, right? Like you see and hear as you're getting closer to an object that you don't want to hit. And now there's a common placement of multisensory crosswalks in most towns where you see either they have the lights flashing, walk, don't walk, but they also have sound, and sometimes they even have these like haptic pads at the bottom. This is all because multisensory information could be the difference of 100 milliseconds in your reaction time, which could be the difference between you getting hit by a car or not. So when you receive two sources of information, so let's call it a light and a vibration, because I'm going to specialize in visual somatosensory integration, so it's all about lights and vibrations. So when they're presented at the same time, they offer what's called redundant information. So one event happens where things light up and flash at the same time, but the fact that it's happening at exactly the same time, it gives you double the amount of information, which allows you to respond to it significantly faster than to either of those constituent unisensory modalities alone. This phenomenon, it gives rise to a redundant signals effect, and I'm going to spend a little bit of time trying to help you understand how we can measure multisensory integration using these various probability models. It's called a race model or the Miller's inequality. In the field, many people say they want to violate the race model, and I'll show you what that means. But I thought it would be very important to figure out a way to quantify multisensory integration, and I'll show you how that's happened over the past 15 years. So legitimately think about a race, right? We have two cars, the red and the blue guy. And the idea about a race is that someone's going to be faster and somebody's going to cross that finish line first. That is the winner of the race. So if you could picture this red guy as the somatosensory guy and this blue guy as the visual guy, you should say, well, if I present both at the same time, whichever signal makes it to my brain and allows me to respond faster is the winner of the race. So I am going to respond, and that's going to be either my response to the visual or to the soma guy alone. So these race models are really probability tests that use separate signals from different activations by the individual sources of information. And they say when these two sources of information are presented concurrently, the one that crosses the line, obviously, the finish line first, is the one that produces the response. Now that's okay, great, but that's not what we're really going to study. What really happens and what you really want to see in your data is support for a co-activation model. You want to see that there's some visual guy and some soma guy. They're both getting presented, and what's happening is that the information from both pieces come together synergistically and rocket across the finish line, right? So this is saying that your brain actually trumps from receiving the redundant information, and it leads to a facilitative advantage. So it allows these sources to combine, typically non-linearly, and that are the facilitation and the reaction time to whatever you're receiving will get to the finish line faster than either of those constituents alone. So when we study multisensory integration, we use these probability models. I'll show you a little bit about how calculating it, because I could do a whole lecture on it, which I'm sure wouldn't be as fun. But what you really want to show is that you violate the race model and you support co-activation, because the idea is I want to prove that when I present multisensory information, there is truly a benefit to receiving that. So how we measure it in the lab, typically, is you'd have a person sit in a chair, they'd have white noise over their ears, so they couldn't hear the vibrations as they were coming on because we're just blocking out the sound, sorry guys. And they're sitting with their foot, their right foot here is over a foot pedal, and their eyes are fixated on a bullseye target, and their hands are on these two cubes, right, left and right. They have their thumb right under this little blue LED, and in the back is a little square box. It's a pager vibrator, you can see it sticking out here, that their index finger is on. Very simple task. Let's call this basically not even a cognitive task, because it's basically whenever something happens, whether you see something, feel something, or see and feel it together, just respond as soon as you can. So the stimuli always come on bilaterally. So if you have in the first case, I'm sorry, up here in the first case, you have two lights that come on, the blue lights come on together. And then there's some random interstimulus interval between 1 and 3 seconds to avoid anticipatory effects. And then the next random target might come in, and this one is just a somatosensory where both of these boxes vibrate. Again, they have a 1 to 3 second random trial interval, and that's their response window. And then the last condition is a multisensory. So in the course of this 10-minute experiment, they're receiving a total of 45 45 stimuli. 45 visual alone, 45 somatosensory, and 45 visual somatosensory. And all we're doing is recording their reaction time. As soon as you feel it, as soon as you see it, respond as soon as possible. So what that provides us is with this nice matrix. So we're able to take the 45 responses, which obviously I couldn't fit on the screen, but you get the idea. And we sort them from fastest, their fastest reaction time, to soma, all the way down to their slowest. We do that for each of the 3 conditions, right? And so what we're able to do using probability models is calculate the probability of a response for any one of these 3 conditions, given all of the response time for that one person. The really cool thing about this experiment is that no matter what you do, your 2 unisensory inputs always serve as the control for the multisensory guide. It's always they're coming alone or they're coming together. And you're always looking at the person's reaction time within their own profile. So after we determine the probability of each thing happening, we sum it up. So we have cumulative probability for all three conditions. And what we're able to do is use the cumulative probability of both the soma plus the visual with a maximum of 1, because each of those could have a probability of 1 that would sum to 2, and it wouldn't really make sense. Because what we want to do is take whatever we predict from the two unisensories, and we want to subtract that from what actually happened, the actual multisensory cumulative probability. So the test of the race model, which we want to violate in support of coactivation, is really just the cumulative probability of the actual multisensory event minus the two constituent. And anything that is positive, like this very nice positive peak here, supports a violation of the race model. So this person, if this was one person's multisensory difference wave, would be showing very great multisensory integration during the fastest, nearly 20% of reaction times, suggesting that on most of on these trials, they were able to be significantly faster when receiving multisensory information compared to the two unisensory. And another way to sort of depict this, now that I'm learning about violin plots, is here you can see the reaction times. The lines represent the mean, the actual numbers are down here. But look at the last guy. The last guy is, and this is almost 250 people. The last guy is the lowest. He's the fastest. The range of reaction time for visual somatosensory starts at the range starts at 213 and goes up to 1019. But the mean is so much lower. It's 369 compared to these two means. So what I'm actually showing you in that positive peak of the race model is mainly we're honing in on what's happening in the multisensory condition that is not happening or is not captured by the other two unisensory. Because if you were to think about these reaction time distributions as, bell curves, there'd be a point that they'd all overlap. But we're really looking at the fastest beginning part, and that's what we want to capitalize on, because we began to found that not everybody integrates. And that's where the problem is. So how about I pause there if there are any questions? So I don't want to get too mathematical, but I want to set this up because we're going to be looking at these difference waves throughout the course of the presentation.
So I just want to make sure when both are together, there's antagonism.
There's
Antagonism.
no, there's synergy. They work together to cross the line together. Yeah, it's a good thing, but not everybody has it. And the question is, if you don't have it, is there antagonism or something else happening, like people being overstimulated and sort of distracted, which is what we want to understand. So, okay, so back in the day when I was a postdoc, that's so old saying that, I would process this information by hand. So I would be looking at Excel sheets with matrices of reaction times and looking at these waves. And this is one waveform represents almost 300 people, but I'd be looking at one of these for everybody. And they always didn't look the same. There were ones that were really like scary looking, ones that were super positive, super negative. And I was like, what's going on? So what I wanted to do was combine everybody to see what happens. And I can say in almost 300 older adults, there's this very nice reaction time facilitation, right? A violation of the race model in support of this multisensory integration happening in almost 300 older adults. And it's over the fastest 10% of reaction times. So overall, you would say, okay, Jeanette, great. Everyone's integrating. So what? Everyone's not integrating. So every percentile bin has a data point. And so I said, rather than using these simulators or all these other ways that people try to figure out what multisensory integration is, let's be empirical here. Let's actually take the cohort's average data and understand the sample better. And I said, all right, so we have evidence that there are these three main points where people demonstrate as a whole multisensory integration. So we'll talk about what the continuous measure is, but for descriptive purposes, I said, you know what, let's just sort of separate this out. And we say, if all three of those points are positive, we know that you are an excellent integrator. You're doing very well at integrating information when presented with 2 versus 1 modality. Then I said, you know what, even if you have 2 points, you're still integrating very well, because this very first point is actually only indicative of the very fastest multisensory, or the very fastest reaction time in general. So we'll cut you some slack, and if you have 2 points, we'll say you're still a good integrator. But if you only have 1 or not even any points that are positive, we know that you're experiencing some problem integrating information. So I took those 289 people, And I'm going to show you what the waveforms look like if you separate them out by one of those 4 classification systems. So this is the area under the curve for the group. So this is the continuous measure of magnitude of visual somatosensory integration that we'll talk about. But to sort of show you what happens, this is all those 289 people separated out by whether they had 1 point, no points, 1 point, 2 points, or 3 points. And what you can see is those people who are superior integrators, look how high the amplitude, look how high the amplitude is. Look how much longer the reaction time facilitation goes from 0 to 0.15. Even if you have 2 points, you're still integrating nice and have this very large area under the curve. But if you start only having 1 or no points showing multisensory integration, these are the people that have poor and deficient multisensory integration. Then you might say, okay, so not everybody integrates very well. So what? So what is actually a big problem. So area under the curve, this is the continuous measure for multisensory integration, and this is how I'll refer to the magnitude of multisensory integration. So my biggest question was, well, why is this important, right? We have sensory integration. Some people can't do it. What does it mean? So I wanted to figure out what it meant in terms of looking at it as an independent variable that could predict some motor responses. And what we found here is even after controlling for everything that's in white, all of those covariates, we found a significant relationship between how well somebody integrates, that magnitude of multisensory integration, and balance. And balance here is defined as the unipedal stance test. And you can see here, just for visual perspective, based on their classification, if they were superior, good, poor, or deficient, as multisensory integration goes down, so does the amount of time that they can stand on one leg. So this is from that group of 289 people. And we were fortunate enough to actually have falls data on these people. So we had, when they came in, we had whether or not they had reported a history of falls, but we also called them every 2 months to track whether they had a fall in the future. And we did that for a mean of 2 years. And what we found using our Cox model here is that the people who had that nicer positive peak, that ability to show that they could benefit from multisensory integration, were the people that went on to have less falls. So 76% of the people who had good integration did not have a fall in 2 years after we tested them, but 24% who didn't integrate went on. So 1 out of 4 went on to have a fall of the non-integrators, and that's a big number. And it's also consistent with the national sort of averages, somewhere between 1 in 4 or 1 in 3 people go on to have a fall in the year. So also working with Dr. Joe Verghese, who's like an international gait expert, also wanted to know, okay, is it just balance? Does it also have meaning for people's walking ability? So we had them do a simple walking task. So you can see they have an instrumented walkway, I think similar to the ones that you guys might use from PK Mass. They're asked to just walk at their regular pace, and we capture steady state gait. And we wanted to know, is multisensory integration linked to gait? And then this mat gives you like 100 variables. So it's way too many to actually look at independently. So we've done some PCA analysis and said, you know what, we'll look at the 3 main domains. We have the spatial aspects of gait that fall under the pace domain. We have the temporal aspects that fall under the rhythm domain. And then we have a variability measure that's made up of 1 spatial and 1 temporal domain. And so when we looked at that, we found that, yet again, people who could not integrate well had worse pace. So that meant that their gait was, their strides on their gait were longer, their gait speed was slower, and they spent more time of their cycle in double support. So do you know, I didn't know this, but when you're walking, there's a point of time when both of your feet are actually touching the ground. And that's bad. As you get older and get slower, the more time you have with both feet on the ground, the more time you're not actually moving. And that could be a predictor of falls in and of itself. So the people that weren't integrating this visual and somatosensory information that from an evolutionary perspective should be a benefit for them were the ones who were actually having worse gait, worse balance, and more falls. So when I was trying to figure that out, first I was a little upset, like, well, what happened to rhythm? Why didn't that make a connection with multisensory integration? And the more I researched it, the more I was like, oh, of course it doesn't. It's more like brainstem and spinal network stuff. When you look at PACE is aligned with some of the more cortical and subcortical areas of the brain, like here, the cortical frontal motor primary sensory areas, superior to temporal sulcus, which is very large multisensory area, and subcortical areas, including the thalamus, relay center of the brain. So it makes sense why these two would map together and why rhythm may not. But the thing about variability is variability was close, and I was like, well, why? If we have something that's significant under pace and something that's not significant in rhythm, okay, fine, this was close to being significant, but it wasn't. But then it has a component of each of these. So when I looked at these two separately, it was still significantly linked to variability of stride length, which makes sense because we mapped onto only the spatial aspects of gait and not the temporal. So now I'm getting greedy because now I know that sensory and motor stuff is linked, and now I want to know, okay, well, what about cognition? Like, does it have a say in this game? And it really does. So here we're looking at that same difference wave, and you can see the dotted lines represents the overall cohort of 345 older adults. And I should mention that all of these older adults joined a study where they were not allowed to have dementia at baseline, but because we studied them longitudinally, there was a chance that they developed it. And because I looked at it from like a mid-year, like the third year of the study, some people, 12 actually, at that year met criteria for dementia. 40 people had mild cognitive impairment, and 293 of them were deemed normal. We had clinical case conferences with neuropsychologists, neurologists. We looked at the neuropsych data and some of the CDR ratings to make these assessments. Yeah.
You showed it once before, but can you just describe exactly what this is showing? Like, what's the, what's that upward blip in these QI? Does that mean that for their fastest reaction times, they responded better with both modes of stimulation, but then for the rest of them, they responded slower? I mean,
so as I mentioned, the multisensory stuff is the fastest stuff. So it happens at the end of, let's call it, the very first distribution, right? For just the multisensory responses. But when I have the visual and the soma, which can start a little bit lower, like a little slower, what we're looking at, where the multisensory stuff happens, it's the very fastest reaction time. So what our data is showing us is that the very fastest, so the 10%, the 10th fastest responses are where we're seeing multisensory integration if it occurs. But we're saying it doesn't occur for everybody. And this in particular is showing you the average of 345 people, and it looks similar to the other one where there's this nice positive peak indicative of multisensory integration. But on this slide, you can see that that is only really true for the people that have normal cognitive status, because the people with MCI have a very, very slow, late, tiny dip of indicative of some integration, but the people with dementia don't integrate at all.
And what's the dip towards the right?
This dip here?
No,
The,
the very large,
oh, over here?
yeah.
That's where the three, if you think about the three bell curves, they all overlap. So there's no difference because everything has reaction times in a range that overlaps for the multisensory, for the soma, and for the visual. So you wouldn't expect integration to occur at like 5 or 6 or 700 milliseconds, because you'll have responses to each of those sensory stimulation. Remember, I have 45 reaction times, so there's going to be some range. What we're saying is that on a whole, the fastest responses that you're going to have in a person's profile are going to be linked to the multisensory
So
condition.
why a big dip or a small dip?
These dips here?
Yeah, what is the difference between, at that
Well,
point, does that mean anything?
No, it's really just the difference in the cumulative probability. So if you remember, I showed you that we're taking the two unisensory and summing them and subtracting that sum from the probability of what happens when it's molt. So the more negative it means is that they had a longer reaction time to the multisensory stimuli in the middle of the range than to either of the unisensory.
As if it confused them or something.
Distracted.
so
They didn't benefit.
so the fastest ones get faster with multi-center because of multi-center integration.
Yes.
But then actually, there's many stimuli that are slow. The majority of stimuli are responded to slower.
And that's to be expected, because if you're looking at the range, that's very different than not fishing, but honing in on where the multisensory stuff should happen, right? Think about if you're taking a test and you're responding, right? You're gonna have a series of reaction time. You're gonna be in some sort of a range because your attention might be shifting. You might be doing this test on the phone and a phone call comes in, or you might be sidetracked. So there's some variability, we know that. And the point of this whole thing is that if I didn't present the two at the same time, you would not have those fastest reaction times. You would just be at whatever you got from the visual alone or whatever you got from the somatosensory alone. Is that cleared up? Yes, no?
Yeah, I'm just surprised that like, you'd think it would be more. Some would be faster, but then everything else would be the same, or like, but it seems like everything else is kind of slower. If that's what I just want to make sure I'm interpreting.
But yeah, but this is not in everybody. So you can see that based on the diagnosis, it obviously changes, right? But it all has to do with the fact that you're not, these are not the reaction times. This is the cumulative probability of a response happening within the entire range of responses over all three conditions. So when we did our mediation model, what we found is that whether or not you had cognitive impairment as MCI or dementia compared to normal cognition, it actually significantly mediated the relationship between both the multisensory integration and the gait and the balance. So what I showed you before, that association that was significantly linked between multisensory integration and the two motor outcomes is actually dependent upon whether you have good cognition or not. So when you don't have good cognition, you also don't have good sensory integration or good balance or good gait, suggesting that they all sort of jive together. So visual somatosensory integration is largest in older adults with normal cognitive functioning. Okay, so we took the 10 top medical or geriatric conditions, and we wanted to know, is multisensory integration affected by any one particular medical diagnosis? So does anyone have a thought as to, and maybe you saw it already, but as a thought to what sort of medical diagnosis might impede our ability to benefit from multisensory integration?
Hypertension, diabetes.
Did you raise your hand? No.
Peripheral neuropathy.
Peripheral neuropathy. See, that would have been one of my guesses, or like arthritis. Any other? So it's not hypertension, but it is diabetes.
Well, comorbidities.
So we looked at medical comorbidities, and diabetes was the only one that significantly affected how much or how well you integrated.
What about medication? Some people,
Yes.
sleeping pills and antidepressants and so on.
So we didn't hone into all the different types of medication, but in this one study, when we found out that only diabetes was the only thing that was sort of determining whether or not you integrated, we looked at what types of medications they were on, and we found that those people with diabetes that were dependent upon insulin, look at this, they don't integrate at all. Those that have diabetes but are not on insulin have a significant reduction. The difference between this guy and this guy is huge. They're still integrating, so they're still getting by, but it is way reduced. And the people that are on insulin are done. So starts raising questions like, what's going on? And what I was thinking is, wow, these people with diabetes, very reminiscent to the people with cognitive impairments. So I wonder if there's some similarities. I know that people sort of talk about diabetes and vascular, cerebrovascular as like the dementia type 3. So I think in some of my future work, I'd really like to assess this further and figure out what exactly is going on. What is the mechanism that's causing people with diabetes to not integrate? And, it's true. A lot of people with diabetes have neuropathy, right? They have visual retinopathy, they have neuropathy in their hands or diabetic neuropathy in their feet. And I wonder if that's contributing. So just to recap, we've shown that multisensory integration is different in older adults. Not everybody integrates. People who do integrate have better balance, they have decreased falls, and they have faster gait velocity This whole thing is mediated on whether or not they have any cognitive impairments, and it is actually, I didn't talk about, but it's linked to attention abilities on neuropsych tests. And so what I think is going on in terms of overlapping networks, you see all of this information is coming right from the hand and the eyes, and it's working its way up to sensory and association areas. But I really think that it's somewhere in the prefrontal cortex that once this area is disrupted by something like Alzheimer's disease, that we start losing our functioning across all three systems, sensory, cognitive, and motor. And that's really what I set out to do in my R01 because of some of the preliminary findings that we have from the magnet. So I actually have an apparatus in the magnet that allows them to do this test. It uses pneumatic, that's weird. It uses pneumatic little balloon shaped stimulators that they blow up in your fingers, very small. So it gives you a way of giving a vibration to their finger or sensation to their finger. And then they have their goggles and they're like lying in the scanner with their hand on the abort button. Their other hands are on the response pad and masking them as soon as you see something or feel something or both. Please make sure to respond as soon as possible because I want to know where in the brain this is related. And so when we looked at just the structural images, you can see both from a volumetric and a thickness sort of perspective, anything with a p-value on this graph is showing that it is significantly related to their magnitude of multisensory integration. What I thought was really interesting was that this integration was significantly related to areas of the brain that are known to be affected by Alzheimer's disease. And I was wondering if that's also contributing to the cognitive impairment. When we actually got to look at the areas of the brain that lit up using the functional MRI, we found that there was indeed areas of the dorsolateral prefrontal cortex that were associated, less bold signal was associated with less integration. So in support of the theory that that I think that this has a major role in whether or not somebody goes on to integrate or not. So this is probably the work that I'm most proud of. I think after 15 years, we've sort of been building up to this, but as many of you know here, there's a real problem with Alzheimer's disease and it really alters sensory processing. And some people argue that it's affecting sensory areas of the brain well before higher order cognitive areas of the brain. So wondered if our research on multisensory integration could be used to predict whether or not somebody might be at risk for developing Alzheimer's disease. Like, could we have some tests like what I have, which is not really super cognitive, as opposed to like other neuropsych tests? It's definitely not invasive, but could we use a 10-minute test to be able to predict whether or not somebody goes on to have Alzheimer's disease? So what we did was we gave 243 people who gave us blood samples, went through that same sensory test, and we looked at their magnitude of multisensory integration, and we wanted to know if it was related to their amyloid beta probability score. So from their plasma, we were able to get a composite score that took into account their A beta 42/40 ratio, presence of whether or not they had the APOE4 allele, and their age. So three main biomarkers for Alzheimer's, all combined in one score, gave us what we call an amyloid beta probability, APS score. So what you're looking at here is the 243 people. You see that same positivity in the dashed line. The people who have no signs of amyloid, as evidenced in their plasma, are the ones that are integrating the best. The people that are in this intermediate gray zone, where they have some amyloid, but it doesn't reach the threshold of being positive, have a significantly reduced integration. And those almost 40 people who were amyloid positive, we were able to show on this test don't integrate at all. So this was highly significant, 0.01, even after controlling for gender, ethnicity, years of education, medical comorbidities, whether or not they had visual impairment or neuropathy, their overall reaction time on the test, and their diagnosis. We just published this last week in Alzheimer's and Dementia, so it's really important. And what I wanted to do from a confirmatory perspective is forget the APS score, go back to the clinical case diagnosis and see if it matched. And our findings are very similar here, that based on clinical case conference, you see the same sort of pattern where those that have normal cognition show the best integration, and those that have sort of MCI and dementia don't integrate at all.
Let me go back to the previous slide. for a
Yeah.
second. The big difference between unstandardized and standardized coefficients. And, you know, there are some people are very critical of standardized coefficients because they vary across variables.
Okay.
So sometimes you see a big difference, it's just a matter of one variable being more variable than the other one, distribution being more variable. So my own feeling is that probably the unstandardized probably better than the standardized, but I'm not sure.
The unstandardized coefficients. So the very first model doesn't have any covariates.
Excuse me, you talk about standardized has two meanings. One is adjusted. Is that the meaning that you use?
No. So the first model here in this regression is just looking at the association of magnitude of VSI with our amyloid probability scale. The second model is that same thing, even after controlling for all of these in the models. So each of them have their own statistics with it, but this is the main one of interest. And that is still very significant after controlling for all of these variables. So you can't just say, well, by virtue of having a clinical cognitive consensus diagnosis of diabetes or of dementia, that was what was driving the effect.
Thank you.
Yep, no worries. And this is unpublished data, but what I want to just drive home is that I know I've been showing you the area under the curve using these line graphs, but if we look at it as a bar graph, and you can see whether or not person has normal cognition, MCI, or dementia, and if you break it down as to whether or not they also had a fall, you can see that all of the fallers captured in red had 50% worse or more reduction in magnitude of integration compared to the non-fallers. And that is consistent across all three diagnoses. And this is just another slide showing you based on fall status. You can see an increase. The fallers have an increase in their APS score. So I'll just skim through some of these next slides so that we have some time. So based on all those findings, we have an R01 at my former institution, Einstein. We have an intensive battery. They come for 4 days a year where they look at sensory, motor, cognitive, neuropsych. They see a nurse, they get blood drawn, they have an MRI. And what they're doing is we're looking to see if we can see a visual somatosensory integration is a novel marker for Alzheimer's disease. The three main aims that we're looking at, is to first identify the actual areas of the brain that are related structurally and functionally to multisensory integration in people with preclinical AD, and to determine whether functional multisensory responses in prefrontal cortex of the brain actually go on to help predict who's at risk for fall in people with preclinical AD. And then the last one, which is sort of the paper I just published, was to determine whether AD pathology actually influences the magnitude of multisensory integration, which we know it does. So we had various inclusion and exclusion criteria to be included in this study. We can circulate these slides later because we're running out of time. But just to give you an idea, this is why we see them 4 times a year. They go through all of these tests. And I will say that they actually don't complain too much about it. Some of it's actually fun for them. They like getting out of the house. They like doing the pen and paper tests. They like working with like the younger grad students. It's really a breath of fresh air for them, which is surprising. But you do have a couple of people that are really anti going in the magnet or not really wanting to give blood. So briefly, the app that Jennifer was talking about is called Catch You actually before you fall. The work that I do here is really significant because it's really in memory of my grandma who had a fall and we wound up losing her several months later. So everything I do from the science world is sort of dedicated to her because my main goal is to really help older adults not experience this debilitating loss of a fall. It's a big problem. I was telling Frank earlier, we don't do enough to sort of prevent them. We have annual wellness visits where we ask people, do you have a history of falling, or, do you have a fear of falling? And we get the answers, but we don't do anything about it. So it's not like it's going on to help them not have a fall. We're just sort of capturing their data at one point in time. And the fact that we don't have any quantitative metrics out there to actually figure out if somebody goes on to have a fall means that we can't really introduce an intervention. So based on this research that I just presented to you, we wanted to know, is there a way to get this apparatus out of the lab to the hands of people so that we can actually test in real life whether or not somebody is, at risk for a fall? So the idea is that a doctor could order this test. They'd be given a 1-pager that shows them their reaction times, that shows them that they would be obviously taught how to read this, but you can see overall this person's not integrating well at all. They have very long reaction times. The reaction times to the visual and the soma are equally long as the one to the multisensory. We would expect some, maybe half of this if they had a facilitation, which they don't. And then you have this very large negative dip with no positivity at all. So this person is indeed at risk for falls. So all we want to do is point the doctor in the direction of, what can you do about it? These people are at risk for falls. Hey, here are the guidelines from the CDC STEADY program. Get your patient involved in physical therapy. Figure out if you can get them to join an exercise group, have them go on to do some Tai Chi, something that we know can help them with their balance, and then assess them again after 6 months. If nothing changes and they're still at risk for falls, then you have to figure out if there's some other intervention that could help for them. So this is just some of the work through the years that we've published on this. And we have a large team that's really trying to push this out there so that we can get to the people who need it the most. Our first idea is to get to people that are in older care communities, geriatricians. We're also talking to some telemedicine companies. And then eventually we'll hope to get this direct to consumers, because falls are a huge problem. And we have a tool that just needs to cross the research barrier and make its way into the commercial world. So just real quick end with what I was explaining to some of you earlier. This is the plans for a mobile multisensory lab that we're building at Stony Brook. And basically what you're looking at will be a racetrack, and this will be one continuous area of walking. And we'll have older adults, we'll be capturing steady state walking on what's blue. And they'll be wearing a mobile EEG. They'll have a multisensory vest and a hand response, and we'll be capturing electrical and behavioral data as they walk around the track, and in normal conditions and during multisensory conditions. And we'll be able, through the use of an eye tracker, be able to figure out if there is some sort of competing attentional demands that make them focus as to whether or not they should be more concerned about their gait, or if they're really competitive and really want to do well on the game part. So this is something we're starting and should be able to test participants by the end of this year at Stony Brook in the new lab. So wrapping it all up, why should we study integration in aging? Because it is possible that there is some underlying neural mechanism responsible for age-related declines that are concurrently affecting sensory, cognitive, and motor functioning. It is influenced by cognitive impairment. And my future directions really include taking a deeper dive to understand some of the neural derailments that happen during preclinical Alzheimer's and Alzheimer's, and to find ways to augment existing interventions so that we can prevent disability, optimize independence, and further aim to enhance quality of life in older adults with and without Alzheimer's. So I thank you all very much for your attention. Special thanks to Dr. Zealand Lynn for having me here, and to the whole center, and Mindy for helping me set this up. And thank you. Lots of questions.
Yeah, and I think we have some questions in the room. We also have a question online. So Richie, let's start with you and then we'll go to the online.
Fascinating, and I think it makes a lot of sense, but I'm wondering, in your data, you simply have reaction times. Have you looked at simple reaction times as predictors of all these outcomes? And do you know that this more complex analysis of them is actually superior as a practical matter?
So meaning, instead of
People who
using,
react slowly may fall to a simple stimulus.
no, I didn't look at that, but I did always control for overall reaction time across all conditions for everybody in all of the analysis. So this is still coming out significant when you control for that.
It would be simple. I mean, it is such a simple test. It might prove to be pretty good all by itself. And
So
you do it.
So you're wanting to know if just reaction time in
We react
general.
Slowly fall. And
Yeah.
augmented and so on.
Yeah, and that's the thing about falls, right? I mean, this is one aspect of it, but falls are so multifaceted. We know people with hearing loss fall. We know people that have poor motor outcomes in general fall too. So this sort of adds to the mix, but no, I didn't look at that. We could check it out for sure.
Yeah, be interesting.
Thanks.
Yeah, if we even, taking this, expanding on Dr. Shadow Rich's idea, look at the relatively simple test. Because you're going to have those more complex tests. And look at just defense validity, predictive validity. A couple of questions, how many people are going to be included or have been included?
So the
Last study you mentioned.
the last study is gonna be a little over 200 older adults, half with normal cognition and half with preclinical.
And how long does the exam take? What is the duration of the exam?
To do all of those things, they come in 4 times, about 4 hours each with breaks.
And what is the reference population? Who are those people?
So we have, based on their cognitive status, we have people, we compare the people with mild cognitive impairment to those who do not have it.
So it's a convenience sample?
Yeah, yeah,
Convenience,
right.
which is okay.
It's always,
Studies we don't need the sample.
yeah. We've not gotten to the point where we could do like a very large epidemiological study, which could be
One last
amazing.
question. Modification by age. Do you believe there will be some moderation by age?
I don't know, because age is a funny thing. We have a geneticist and biologist at Stony Brook, right? Who's looking at differences between biological age and chronological age. And, you could be 65, but out there living like a 95-year-old. So there are, I mean, we control for age, but there are definitely differences across it.
Yeah, you mentioned stages, but not everybody has the same stage of transition.
Right.
Would that be taken into account?
So in the newest study, we won't have anybody with dementia at all.
Oh, I
They
see.
will only have mild cognitive impairment because we started a new study and that's an exclusion at baseline. Yep.
Did you ever look at the real world behaviors in terms of how much they walk and what their activity levels are?
Outside of the lab,
Yeah.
no, we're starting to.
Yeah.
That
I
was,
mean, we published a number of papers on this, that like the discrepancy of risk factors that are judged by the amount of falls you have over a period of time. And the rate of how you would fall based on your exposure to falls, based on how many steps you take,
right.
are very, very different. In fact, they're almost sometimes completely different.
And
So-
there are also some people that
so
never leave
because-
their house, right?
Because naturally, people who have a dangerous gait, they realize that, and they'll often restrict their walking.
Right,
And so, so the analysis of just looking at falls over a period of time is really only part of the story.
sure.
It's often a predisposition towards falling and either a lack of recognition or an imperative that they have to keep on being active because of their life circumstances. And so you're kind of integrating those two. So if you really want to get at people who are dangerous walkers, you'd want to look at people who have more falls per the amount in.
Yeah, and we have some.
Which is probably what you're getting at. but-
Yeah, I have to start somewhere.
There's a question online that says, did you look at multisensory integration in people with depression?
No. In other cohort, we did give the geriatric depression scale, and on a whole, nobody actually met criteria for depression. It wasn't an exclusion criteria, but it is something that I think would have an effect on it. Sorry, you've been very patient.
I was just curious, one of I think you mentioned you did like 10 disease analysis to see, I was curious if one of those was multiple sclerosis.
It wasn't, because we didn't really have anybody with MS and we didn't really have anybody with PD, Parkinson's, so those weren't included. It was more like arthritis, angina, stroke, COPD, depression, which didn't come out positive actually, but again, not in our really cohort, and a few others, TIAs and whatnot. Yep.
When you had the bar graph and the line graph next to each other, the bar graph was specifically showing the somatosensory data next to.
On the report?
Yes, I believe so. I was just curious, for the line graph, is that also showing specifically somatosensory compared to visual sensory
This,
Responses, yes, or is after the multiple sensory responses,
it's just a difference waveform. So it takes the cumulative probability of the multisensory and it subtracts out the cumulative probability of the two constituents. So anything that's left over, in this case, is being, this person's not integrating. So it's all being accounted by the unisensory stuff. When you have that nice positive inflection, we violate that race model, that's where you can say, okay, there were integrated processes. So when it's negative, it's not really. Yep,
So you're looking at the, you know, the amount that they do better, you know, on that left-hand portion of your graph with both stimulators, both stimuli, you're looking at that as predictors of
Yeah.
of their ability to integrate. But then, you know, I think the question was brought up earlier about distraction. Do you ever look at like, you know, how much worse they get with, you know, multiple things and like, you know, like measure their distraction capacity?
yeah, so.
And then look at that as pretty, because it seems like that's pretty bad too, right? Like if they can't handle these multiple stimuli.
Yep.
And they get distracted by them and then, you know, and then maybe they have falls or they have issues with that as well.
But the thing about the stimuli, I mean, and we know it's linked to attention. People who don't integrate have worse attention, right? I'm just trying to get you this side. This one. So a question came up as to why are the older adults with dementia, why is there different weights so much more negative than these guys? And I think you were alluding to that earlier too. And for the longest, I was so fixated on this because if you don't have this, you're not integrating, that we started thinking about ways we could test this. I know it's linked to attention. You have to realize when they receive the sensory information, it is very fast, 100 milliseconds. It's a quick light flash. It's a quick somatosensory pulse. It's sort of, you would think would capture your attention. It's a change in your environment. You're reacting to it. We know that they're not failing the test because they're reacting to all three. It's just that when they get both, they're not reacting any faster. It could be if they have neuropathy that they don't feel it, right? You would say, all right, well, there's nothing to gain. I get everything I need from the visual guide. Or if they have some visual impairments, maybe they don't see it as much. They're getting everything they need from the soma guide. So I don't know. It makes sense that it would be distracting, but I'm trying to figure out why it would be so distracting when you would think that it would sort of prompt them to go. The question is, why is it not? And what other tests it's linked to? I would not looked at that yet, but it's sort of like on our to-do list.
Pablo, did you have a question?
Most of this already.
Okay.
Thank you.
I'll ask another question. Because, I feel like you've given us a lot to think about. Thank you so much. And I'm just even curious about like going back to the beginning. So you're testing the visual systems and the somatosensory system. Like why those systems in general? Have you thought about other sensory systems?
Yep. So in our very first work, we looked at auditory, visual, and somatosensory. We looked at the pairings, all three of those. And we also looked at trisensory, which is all three at once. What we found is that older adults tended to show the greatest multisensory integration when presented with visual and somatosensory. So when you took out auditory, whether it was auditory with somatosensory, auditory with visual, the greatest effects were in visual somatosensory, which I was sort of happy with because it was what I was already doing. And to me, those seemed most important for the motor outcomes that I wanted to study. But we have looked at it, and there are a lot of other sort of studies that deal with more multisensory higher order cognitive tests like illusions that have linked like the sci-fi illusion with more falls. Some of Dr. Newell's work, yeah. So there is some stuff out there.
Thank you.
Great. Thank you guys so much.
Any other questions? Okay, thank you so much.
Thank you very much.
We do have lunch for those who RSVP'd, and if you didn't RSVP, you can stick around just in case we have extras, and you're welcome to that.
Thank you, Clarice.
No, you're not getting it.
Like, I wish that we could do
That's it.
Really bad.
Yeah.
That was awesome.
Thank you so much. I appreciate it.
Incredible.
Yeah.
You know, you're doing incredible English, and it's terribly important.
Yeah. So Dr. Moise is,
I'm an radiologist in a different area.
he's not in it. He's the best at it now.
That's
First of all.
just very neutral,
That's right.
no bias.
Oh, my goodness. Hence the question.
I really enjoyed it. You very interesting, very informative.
Thank you.
Although I have to think about it.
That's the thing. But
Like you said,
like design.
yeah,
Not distance.
that's right. Yeah, so like a profession. But I was thinking about lots of things, yeah, like integration. But not just that, but lots of more things that could get in therapy for cancer, chemotherapy. And sometimes we have a stressful event. The other thing, you know, the cognitive system is important. Actually, I have a fucking balance to help you. And if fighting is safe, it's not science. When I walk fast, my balance is broken. If I stand and walk slowly, then I have to. Yeah. Yeah, it really is.
Slow to start, and once they get it.
All right, very nice. Congratulations.
Thank you very much. That's mine.
Congratulations.
Thank you very much.
MRI. MRI data.
Yes. You know, there's yeah. Are you doing this? Yeah. Okay. Okay, sure. Right, right.
Oh.